Okay, hi guys. So in this lecture we'll be talking more on internal energy, which is nothing but the total of all possible kinds of energy present in the system, which is represented by U. So U is, it can be also written as sum of translational energy of molecules plus rotational energy of molecules this is not clear enough. U plus vibrational energy plus energy due to intermolecular interaction and so on. Okay, so broadly U can be written as kinetic energy plus potential energy. Okay, now let's take an example. Suppose we have a system 1 connected to a system 2 let's say system 1 is hot or high in temperature with respect to system 2. Okay, so heat transfer would obviously take place. It's, let's say it is at T1 temperature and we have some mass here, specific rather heat capacity here and same here. So we can write that, by the way, two systems have the same mass and same heat capacity, so we can write that at equilibrium there would be temperature T established in both the systems, wherein T would be less than T1 here and T here would be greater than T2 here. Okay, so we can write that, let's say this is specific heat. In spite of heat capacity we have a specific heat, so ms delta T from system 1 would be equals to, this is not power, rather it's from system 1, would be equals to ms delta T from system 2 for system 2, because whatever heat which is released from system 1 would be absorbed to system 2. Suppose they are connected via some conductor. Okay, so heat released from system 1 would be absorbed in system 2, hence we are equating both of them. So ms delta T would be T1 minus T and ms delta T here would be T minus T2. Cutting ms from both the sides, we will have T1 minus T would be equals to T minus T2, or we can write that T is equals to T1 plus T2 by 2. So this would be the equilibrium temperature for both of the systems. Okay, so let's say we had in this system we had the same properties like mass and specific heat. What will happen if we have a different system? So in different systems, just have to again evaluate or equate both the heats, because whatever heat which is coming out of from system 1 would be equals to heat which is going to be absorbed in system 2. Okay, so when we equate it, so in there is a different system, so we would have m1 s1 delta T would be equals to m2 s2 delta T. Okay, so we would have m1 s1 T minus T1 would be equals to m2 s2 T minus T2. Okay, now what will happen at constant volume? So at constant volume, suppose we have in the system 1 we have n1 moles. This was system 1 connected to system 2. So here we had, suppose, n1 moles of the first system. CVM is given of the first system. Similarly, we have n2 moles and CVM2 for the, which is the specific heat capacity, or rather the heat capacity at constant volume. So initially it was having temperature T1, it was having temperature T2, and given that temperature T1 was more than temperature T2, so to establish equilibrium temperature, obviously heat which is released from this system would be going on to this system, assuming that no heat is released during the process, like no heat is released to the atmosphere or to any other environmental things, assuming that all the environmental factors remain the same. So we can write that N1 CV M1 T minus T1, rather T1 minus T, because T1 is the T1 is the initial temperature, and so here also as we took that T1 was the initial temperature. I'm writing just because it stays positive. Okay, and this is also positive, and we also did the same for this case, wherein we equated T1 minus T2, T equated to T minus T2, just for keeping this value positive, as we know that T1 would be greater than T and T would be greater than T2, so just for having the magnitude values. So herein as well we will be equating N1 CV M1 T1 minus T2 N2 CV M2 T minus T2. The heat going away from this system would be getting absorbed in this system. We can also write alternate way, that we know that final is T, initial is T1 plus N2 CVM2, final is T, initial is T2, should be equals to 0. Okay, so heat absorbed plus heat released plus heat released plus heat absorbed would be equals to 0. So we can, this is just delta T, which is TF minus TI. Okay, so this is T minus T1, but if you take it to the other side of the equation, obviously this equation is the only one which you will be getting. So I just wrote it directly, but you can also write it or have it from this one. So this is just a mathematical way of representing same things differently. So now what happens at constant volume, constant pressure, constant volume we have already seen. So what happens at constant pressure? So at constant pressure, suppose we have in the system 1, we have N1 CPM1 at temperature T1, and system 2 we have N2 CPM2 temperature T2, we have T1 greater than T2, or even if we don't have, let's say we don't have any such thing, even then we can write that delta Q change in heat would be 0. Okay, for both the systems. Okay, so whatever heat is which is going from first system to the second system would be 0. Heat going from the first system would be N1 CPM1, delta T would be final temperature, which is T minus T1 plus initial plus the heat which is going to the second system, which would be N2 CPM2, delta T would be T minus T2, should be equals to 0. Overall temperature or overall heat released or absorbed considering both the systems would be 0. Hence this would be the case. Next, let us see equipartition of energy. Next concept is equipartition of energy. Okay, so N is the number of atoms in a gaseous molecule or in a gas molecule, number of atoms in gas molecules. Okay, and then total degrees of freedom would be 3n. Okay, and every translational degree of freedom would be directly writing translational degree of freedom would be half kT. Rotational degree of freedom would be again half kT. And vibrational degrees of freedom would be kT, which is half kT for kinetic energy and half kT for potential energy. Okay, and some points here that at very low temperature we consider only translational degree of freedom. Translational degree of freedom. Okay, so with this we come to the end of this lecture. In the next lecture we will be seeing more on degrees of freedom for, we'll be continuing seeing for monoatomic gas, and then we'll be seeing for diatomic gas as well. So till then, good luck and goodbye.